Welcome everybody to lecture 1.3, Control Systems 1. Uh, we have been in the last two lectures briefly introduced to control systems. We have seen some important terminology, right, related to control systems. And we have seen essentially some examples of control systems in everyday life around us, man-made and natural examples wherein we can see the role of control systems and control theory to some extent. And we have seen differences in open loop and closed loop systems, right? So today we are going to talk a little more in detail about the design process, right? The design process that a control system engineer actually follows for uh, for fulfilling his objective, which is to design a controller for a particular system. So I'll continue with the slides that I was showing you on the last turn. So this is the basic diagram from the book, right? Uh, so the control system design process actually consists in the beginning. So the control system engineer is actually given a problem. He is given a plant or a process which he has to control. He has to uh, control he has the objective of taking the plant or a process to a particular uh, 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 to a particular response, right? So he starts with in the beginning. He starts by determining what is the physical system, right? What are the specifications from the requirements? So, for example, in the antenna azimuth control system that we saw, you will basically the control system engineer will try to see what is the physical system, what are the requirements, right? What is the thing that he has to control? What is the mass? Broadly, try to understand the problem. The next step would be to draw the functional block diagram, right? Functional block diagram would basically involve uh, interconnections between different systems, right? And how what is the information flow? What is the flow of the signals from one system to one subsystem to another subsystem? An example of the functional block diagram we have already seen. So this is basically the actual for the antenna azimuth position control system. This uh, this is the layout, right? The detailed layout of the thing, and the functional block diagram is here. So this is your functional block diagram. In the functional block diagram, you're basically trying to see which subsystem is where and where is the information actually going. It is starting from where and where is it going and where is the comparison done and so on and so forth, right? So you have the angular input which goes to the potentiometer and then it converts to a voltage. And so how does the system basically function, right? It is called a functional block diagram because it is not the block diagram in the sense in which we use in the control systems terminology, because we don't have actually the mathematical models of these things right now. We have not done that portion yet. Normally, we'll have when we draw a proper block diagram, we'll have mathematical models for every component that we're talking about, right? And the third part would be drawing the schematic. So this is the schematic, and the schematic in illustrates the scheme of control that we are trying to actually implement. So you draw the differential and power amplifier, you draw the motor, what kind of motor it is roughly, see what kind of control you're doing. You draw the equivalent, right, of the antenna, the mechanical equivalent of the antenna, and other things, right? So come back to the the actual design process. So so the first three steps are basically trying to understand the problem, the physics of the problem, and trying to put it on paper by drawing the functional block diagram, by drawing the schematic, right? The next two steps are actually to mathematically model the thing, right, properly. So you convert the functional block diagram to a block diagram. Now the difference would be that the schematic or the functional block diagram to the block diagram, the difference would be that in the block diagram you have proper mathematical representation of everything that you have actually seen in the and drawn in the schematic. So block diagram is one kind of a model where you'll have blocks connected to each other, and each block would inside would actually represent a system, mathematical representation of the system. You can have a signal flow diagram also, or you can have some other representation which is called the state space representation. So these are different modeling methods. We'll talk about them in detail. Now, if you have a big block diagram, you can reduce it. So this part is modeling, right? Mathematical modeling of the problem. And this part is model simplification. So you are trying to simplify the model, right? By reducing the block diagram. So this is also something that we're going to study in detail in the future. And the last part is analysis of the system and design of the controller. Analysis means that you're trying to see, now you have the system, right? And you have the input. And analysis means you're trying to find out how is the system going to respond. So what is the output, right? And design, the design part would be you have this system, you have this input, you have the output, and you want to basically design the system, design the controller for the system, so as so that the system has the response that you want it to have. So we'll talk about these things in the chapters later on. The chapter on design is the last chapter that we are going to see. So I hope that this design process is clear. Okay, so now let us see how we have already seen to some extent as to for a particular physical problem how we can determine the physical system, draw the layout, draw the functional block diagram, transform the block diagram into a schematic, right? Let us take an example in which actually doing this, right? So there is this problem in the book related to uh, finding the mathematical model for the potentiometer. The potentiometer is a very simple example. Uh, so let us take this example. So and try to find out, try to fit it in the control system terminology that we have been talking about, right? So now this is a, a potentiometer in which you have an input angle, right? And you have an output voltage. So basically what you're doing is you're turning this knob here, right? You're turning this knob, and as you turn it, what happens is that this end here moves, and it moves from say from C to A if you turn it in a particular direction. So when it is at C, you are actually tapping minus 50 volts, and when it is at A, you are tapping plus 50 volts, right? So the voltage that you're able to tap from the moving element through the moving element B is from minus 50 to 50 volts. And say you take 10 turns, so it is a 10 turn potentiometer. You take 10 turns to move from C to A. So how would you mathematically represent this, right? Uh, how would you make the model for this? So if you assume that when you start at position C, so let us first see what is the input and what is the output from this. So this potentiometer is actually a system, right? So it is a system. What is the input to the potentiometer and what is the output from the potentiometer, right? So the input to the potentiometer is the angle theta IT, and the output from the potentiometer is the voltage V0t, right? So this potentiometer actually processes, right, this uh, angular information and converts it into voltage information, right? So I want to make it right. I want to draw the mathematical relationship between theta IT and V0t. So I'll basically convert the functional block diagram. So this is the functional block diagram into an actual block diagram for the system. Okay. So let us now see. Uh, let me drop this to create some space. Let us now see uh, how to do this, right? So at C, say the angle at C, the angle theta with which you have turned the potentiometer is 0 degrees, and the voltage that you're tapping, right, V0t is minus 50 volts. And at A, suppose since you have covered this distance in 10 turns, and one turn is 360 degrees, so you have actually moved 3600 degrees, 360 into 10. So the total angle that you have moved is 3600, and the voltage that you're tapping is 50 volts, right? So from this table, we can actually draw the relationship between voltage and angle, right? So if we draw the voltage on the y-axis, the output voltage, and the angle on the x-axis, we can start with the point where the angle is 0. And when the angle is 0, the voltage is minus 50 volts. So you are somewhere here, say for example. And when the angle is 3600, say for example here, the voltage is plus 50 volts, right? So this is the point. So you actually have a straight line, assuming that the relationship is purely linear. So this is the curve, right? And if you look at this straight line, you can find out the equation of the straight line from this 2-point formula. You can straight away write that uh, V0, right, minus minus 50 divided by 50 minus 50 is equal to theta I minus 0, because the 0 corresponds to minus 50, and divided by 3600 minus 0. So this, when you solve this and simplify this equation, you'll get V0 is equal to theta I divided by 36 minus 50, right? So what does this equation actually hold true for these points? Let us check. So when theta I is 0, V0 is minus 50, so okay. And when theta I is 3600, this is going to be 100 minus 50, so it is plus 50. So this is the relationship. So can we now put this relationship in block diagram form? Right? So yes, we can do that, but we'll need something more than just a simple block, because uh, the input in this case is uh, theta IT goes in, and then whatever goes into the block, whatever signal goes into the block is actually multiplied by the block. So here you can put 1 by 36, and what you get out from the block, this signal here, is theta IT divided by 36. And then this signal has to be subtracted, right? Minus 50 has to be subtracted from it. So you put a summing junction here, plus minus, and subtract, say for example, a signal whose value is equal to 50 volts. It's a constant 50 volt signal that you're having here. And what you're getting out from the summing junction is now theta IT by 36 minus 50. So this is your V0t. So this is actually the block diagram representation for the whole process of converting the angular input to voltage, right? So you actually started from a functional block diagram, Then you made the schematic. This is the schematic here that you have seen. And from the schematic, you came to the actual block diagram of the system, which is here. This is how you can represent a control device like a potentiometer using the block diagram. So we'll be looking at this in more detail in the future lectures. Right. So now let us come to a very important part of this, which is what kind of inputs do we expect, right? uh, in the control system framework. Why are they important? Because we are always talking about uh, inputs being processed by the system, and system output being a response to the input that is fed to the system. So there are certain test inputs that are very common in control systems that we're going to have a look at today. So here are the waveforms, right? These are the important uh, signals, important inputs that we generally see in control systems. We have already seen the step input when we talked about this is the step input when we talked about the elevator example, in which I told you that uh, you have this you have this move this to this side. You have this elevator. You go inside the elevator and you uh, ask, you suddenly press a button. So basically, at t is equal to 0, this is your time and this is your position, right? Elevator position. What you're basically doing is you're suddenly going at time t is equal to 0. You're asking the elevator to take you to some particular floor. So floor number 4. So this is the step input, right? And this is how it is represented. The value of the input is equal to 1 for t greater than equal to 0, and it is equal to 0 for t less than 0, right? Uh, it is not defined at t is equal to 0 because it is not uni-valued at t is equal to 0. It has a number of values at t is equal to 0, and those values range from 0 to 1, right? So you see that ut is equal to 1 for t is equal to 0, and ut is equal to 0 for t less than 0. At t is equal to 0, it has all of these values. Another very important input is the impulse input, which is shown here. So the impulse input is like you're putting a lot of energy into the system at time t is equal to 0. So you're giving it an impulse. That's what the name suggests. So the value of the impulse is infinity, between 0 minus, which is very close to 0 from the negative side, 0 plus, which is very close to 0 from the positive side. It is 0 elsewhere. And you can show that the integral of this impulse input from 0 minus to 0 plus is equal to 1, right? Uh, so it is like putting in a lot of energy into the system and seeing how the system is now responding, how is it dissipating that energy. The other inputs are very simple and they can be derived from the step input. So you have a ramp. Ramp is a unit ramp would be t times ut. So this is called as unit step actually, because the value of the amplitude is actually 1, right? So if you don't have 1 here, you move to some other value other than 1, you still have a step input, but it is not unit step. So you can have a ramp input in which you're gradually increasing the value. So it is t times ut. So the input is equal to t. For t greater than equal to 0, it is 0 elsewhere. Similarly, you can have parabolic input in which the input is equal to half t square ut. That is, it is equal to half t square for t greater than equal to 0, and it is 0 elsewhere. And you have the so you see these in the ramp and the parabolic type, you actually define it for t equal to 0, right? And it is 0. The system is not discontinuous at t is equal to 0. The value at t is equal to 0 minus is equal to the value at t is equal to 0 plus, and it is equal to 0, right? And you can also have a sinusoidal input, which is a very common input that we'll see generally. So these are the main input types that we'll encounter as we proceed uh, in trying to understand this subject. So thank you very much for attending this lecture. We'll continue on the next